Now, I want to announce the talk of Guillaume de Legret. He talks about reverse engineering a Qualcomm baseband, and the question and answer session is at the end of the talk. So please give a round of applause to Guillaume.
Hello everyone. So the topic of this talk is about reverse engineering basebands, and especially in this case Qualcomm models. So, just a little intro about baseband, the baseband world. For people who don't know what baseband is, the baseband processor is
Please go near to the microphone. Please go near to the microphone.
Okay. So it's the main chipset of your phone, responsible for handling telecommunications and everything over the air. It's interface to hardware, and it handles the protocol stacks for the telephony protocols. So, most of the time, a lot of people have a smartphone which is capable of running a separate operating system like Windows Mobile, Android, iOS, etc. But the baseband operating system is most of the time it's always hidden. You don't directly interact with it. You don't have the hand on it. So, the biggest suppliers of Qualcomm of baseband chips are, the leader I think is Qualcomm, followed by MediaTek and Infineon. In fact, I just mentioned a few phones like HTC iPhone, but they are sharing the market across various models of phones. So, this talk mainly results from an observation, which, in my opinion, the hacking phones, it's something quite hard to reach for multiple reasons. Not a lot of people are actually, not like on PC, interested in phones because it's hard to reach. It's a quite close industry. The phone manufacturers don't disclose any specifications. Every baseband model is proprietary. So on the system side, you see kind of a black box running like a horrifying piece of code handling terrifying protocols. If you're just interested in the network side, you go to the 3GPP.com website, and then, it's very discouraging, to say the least. So there's multiple reasons to look into basebands. The main reason would be to understand how a phone really works, because everybody is using phone nowadays, and everybody has a baseband, and it would be kind of cool to know what's really running into your phone. Another reason would be for vulnerability research, obviously, because the code base is very old, like 20 years or much. It's very big. The network protocols are very complicated, so it has a good potential for finding vulnerabilities into them, and also for SIM unlocking, for example. So there has been prior works on baseband exploitation, for example. So one of them has been presented last year at the 27C3 by Ralph-Philippe Weinmann, who reported vulnerabilities in Infineon and Qualcomm basebands. But there is no much detail actually on what is the environment, the code environment of the baseband. And in this context, I think exploitation is almost impossible. Anyone who has done a little bit of exploitation knows that you need to know at least in which architecture you're running, what is the operating system, the memory, where you can jump or not, etc. So in this manner, there is a clear lack of literature about baseband. Well, for example, last year there was this presentation about SMS ODEF, where they took all phones, they deployed a nice fuzzing architecture with OpenBTS, and they began to fuzz the phones just to see the result. And as a matter of fact, well, almost all phones has crashed or bricked, but there was no really exploitation behind this, because people who were presenting this talk could not get the end on the system of the phones. So it's very interesting to know that you can find vulnerabilities in this manner, but if you can't exploit them, you have to, at the very best, classify them as denial of service, while they may be exploitable, and that's quite well. So about this talk, I will be presenting what I've done on a USB 3G stick, which is a quite common 3G USB stick you can find on eBay or from your phone operator. I will describe, so it's a Qualcomm baseband inside, and I will describe the operating system running behind this, and how it's possible to develop a debugger to do live debugging on the baseband, which is quite necessary if you want to, to reverse the baseband and also find vulnerabilities. So, well, maybe I need my sticks, you know. Sorry. So yeah, so this is the stick actually. In France, you can find this stick with France Telecom, Orange, sorry, which is the main, well, the leading phone operator in France. I'm not sure the stick is actually working on American frequencies, but there are closed models. Well, it's the name is it's an option stick. It's an Icon 225. It's a 3G USB stick with a Qualcomm inside. The Qualcomm model is MSM 6280. You can find inside an ARM v5 processor and 2 proprietary DSPs for processing the audio signal and the modem data. So it's not the newest USB stick you'll find in, for example, on eBay or in a shop. It's dating back to 2008, and well, the kernel which is running inside it has quite evolved since this. As far as I know, and as I've seen now, well, Rex is the name of the kernel in the baseband, and it's not now. It's an hybrid kernel which is coupled with Oki L4, which is a proprietary derivative of L4 Pistachio. So, well, if you plug a USB stick on your computer, what happens? Well, basically, you have this emulated serial port over USB, which allows you to talk to the stick and passing 80 commands. So, like for example, 80 plus cpin equals 1, 2, 3, 4 to unlock the same. Well, the stick is only supposed to carry packet data over 3G. In fact, it's only supposed to do this, but the manufacturer has just taken the baseband of a full-blown phone and put it into a USB stick. So when you look inside it, it can also do circuit switch operations, which means voice and such thing. The only difference with a phone is that obviously you have no screen, no speakers, and no microphone, and no GPS and such things. If you plug this USB stick in your computer, you will see, in fact, 3 serial ports firing up. The first one is used to pass 80 commands to the modem, and also packet data if the serial port is multiplexed. The second port is only used for packet data when the ports are not multiplexed. And the third port, which is interesting, is a channel to a Qualcomm diagnostic task, which is something which has been left by Qualcomm engineers to debug the baseband. So how to enable the diagnostic channel, it's very easy because, in fact, on this model, it's directly accessible. You can directly pass commands to the diagnostic mode. And on some phones, I've seen you might need to send a strange AT command like $80 QCDMG to activate the diagnostic mode. So, so it's a serial port, so you can pass data into it, but there is a protocol, and the protocol is fairly simple. It's not documented, obviously, because it's an engineering protocol from Qualcomm. It has been partly reversed in a modem manager. If you look into the source, there is a directory named libqcdm, where you can find part of the protocol. So you have begin and markers, 1 byte indicating what is the command, and variable parameters, like depending on the command, actually, and a CRC. There is a lot of commands in this diagnostic mode, and actually some of them offers direct access to the baseband memory. So, for example, the second command reads a byte in memory, and the command 5 writes a byte in memory, but there are like hundreds of commands. So from this, it's directly possible to byte by byte dump the bootloader at FFFFF 4 zeros, which is the entry point in ARM. And you can also dump the whole system memory from 0 because it's loaded in memory. There is also a second mode, which is accessible from the diagnostic mode, which is called the downloader mode. It's a mode which is specifically designed to write a piece of code into memory and execute it. When you enter this mode, you have only 2 commands available, write the data and execute at address. You can only write in a hard-coded range of memory, which is quite small. And to get to this mode, you have to go through the command 58 of the diagnostic mode. It's also enabled when the system crashes, and on some HTC phones, like the HTC Desire Z, I think, you have, when you boot your phone, you can hold volume up, volume down, and power during a few seconds. Then booting, you'll see 5 vibrations. If you plug the USB cable, sorry, on the phone, you'll see a serial port, and this serial port offers the downloader mode. So you can push data and execute in the baseband. It's directly accessible, it's free. But in fact, you do not really need this, since you've got unlimited read and write access in memory with the diagnostic mode already. But if you don't get this mode, you can try the downloader mode. So, as I said, you can dump everything in RAM, in the baseband. So you've got some kind of a live memory snapshot of the memory, which is nice. It's not actually a real memory snapshot, because each time you call to read a single byte, the task which is handling your request will have been scheduled by the operating system. So the image you get might not be totally coherent, but in practice it's fairly efficient. And what is nice is that you can also do this by dumping, for example, a firmware upgrade and pass it into IDA Pro to look inside the system. But with dumping the memory of the baseband, you also get access to the BSS section, which is empty in a firmware upgrade, obviously. So you get access to the stacks. You have the backtrace of the stacks. You have the heap. You have everything, any global variable in memory, which is directly accessible with the right values into them. So it's it's a lot of information actually, and it's very nice. So the memory snapshot is 32 megabytes long. You can find the entry point by reversing the bootloader, and it can be directly passed into IDA Pro. From this point, you can also already see some system characteristics, like all tasks share the same address space. You can quickly find where is the page table and see that the first 30, it's 12, I think it's 12 megabytes of memory are marked as read-only. Everything is running in ARM supervisor mode, and it's presumably compiled with RealView, which is the official ARM toolchain for compilation, with no stack protection, and ARMv5 does not support the XN byte, which is the same as the NX byte on x86. I'll talk about what I've seen from this operating system, and especially the kernel, from this memory dump. So, Qualcomm has developed its own proprietary real-time kernel, which is called REX, standing for Real-Time Executive. The whole operating system, which means the kernel plus the network stacks and any process, is named AMSS. And the system is, you can see directly, the system is made of approximately 70 tasks running concurrently in the baseband. So you have multiple, each task has a different purpose. There are some tasks for handling the hardware, like the USB, the USIM, the DSPs, and so on. And you've got also one task for each protocol stack at each layer, so such as L1, L2, or RMM, for the W, CDMA, and so on. So if you want to, in fact, it's a tiny kernel, but the biggest part of the operating system are the network stacks, which are very, very massive. But if you want to reverse some tasks randomly, for example, I want to reverse GSM L1, you'll need to know what is the API exported by the kernel, so you have a minimum understanding of what the code is doing. So you need to, at least reverse the kernel API, the C library also, and some built-ins, some compiler built-ins like Subfloat. Or C4 long arithmetic operations. So, at first, how the system is booting. So, you've got a primary bootloader, which is stored in ROM, which is immutable, which will read from NAND a Qualcomm secondary bootloader named QC-SBL. This SBL is supposed to load another SBL named OEM SBL, which means the manufacturer of the phone can implement their own bootloader. So, such as, for example, on HTC phones, you've got HBoot, which is the OEM SBL. So you have a menu, a splash screen, and so on. And then it loads the AMSS operating system, which is what is really running in the baseband in the end. And between each of these transitions, you can have cryptographic signatures for each of the layers. On this on this specific model of USB stick, you have no OEM SBL. So QC-SBL is directly loading AMSS, and there is no secure boot at all. So there is no signature. You can reflash actually the stick and run your own baseband, your own operating system if you like. You've got to write it. But well, for example, it could be possible to run a Smoke on BB on this. Well, so the Rex tasks. So you've got, as I said, you've got a lot of tasks, like 70. I'm just talking here about the core tasks of the operating system. Well, you've got the SIP task, which is the idle task, doing nothing. DPC task is used, I'll explain later what is APCs in the Rex world. It's just dispatching APCs across tasks. The main task is the first task loaded, the first task created. It creates all the system tasks and then under the timer events. There is also a task which is used to verify that critical tasks in the system are still alive, a watchdog. And well, you've got data service task gathering any information from each protocol layers and passes them through pipes to create socket and so on. You've got a task dedicated to call management, so for secret switch processing and packet switch processing too, implementing TCP/IP, for example. The kernel, so it's a real-time kernel. The scheduler, well, is quite simple. Well, you've got actually all tasks run in the same address space, and in the same state, the same mode of ARM, which is a supervisor. So you do not need some complex processing to do task switch. You just save the context of the task on the stack, and you change the stack pointer, and you can by this process switching tasks very quickly. There are also there are a lot of fields. I'm just putting the main fields here. Each task has a signal, a set of signals which can be fired or cleared. A task can wait for some signals well, it waits for signals, and another task will send a signal for the task to resume. And the tasks are also, of course, ordered by a priority. So, well, as I said, the context switch is very easy. The scheduler also supports critical sections. The kernel also supports APC, DPC mechanisms. I'm not taking this terminology from the Windows world. It's really called like this in the strings of the kernel. Well, basically it works in the same way as Windows. An asynchronous procedure call is just pushing a new context on the stack of a stack, on the stack of a task, and when the task is resuming, because it was in a wait state, for example, it will execute the call and then resume to its original execution. So you've got a task which is dedicated to APCs, which is a DPC task with a high priority, and it allows a task to execute some code in the context of another task. The operating system also handles timers, of course, because it's a real-time operating system. You can set a specific action to occur at regular intervals. It's very used in the kernel because, in the RF world, you have to do some processing at various intervals. So timers are only by the main task, when it has processed the creation of all the tasks, it's entering a loop, checking for timers to fire. When a timer is triggered, you can, send a signal to a task. For example, a signal it's just like an event, you see. A task can wait for a signal, and then another task can send a signal to another task. So it's like an event. You can trigger an event to a task. You can execute an APC. So, and you can also execute a direct call, which will be directly processed in the context of the main task. So tasks, of course, there are 70 tasks running in the baseband, each for one protocol layer. So there have some communications between all those tasks. So the kernel IPCs are fairly simple also. The main method to communicate between tasks is the use of signals. Like, for example, a task will have a queue shared between two tasks. It will push some data and send a signal for the task to fetch the data. And then the other task can send a signal to say, hey, I've acknowledged the data, I've got it, I can pop the stack. There will also the DS task. So the DS task is a data service task. It's used to unify all the gathering of protocol stacks at the lower layers. It will fetch all the data and put them into pipes so that you can see the data as a continuous stream of data, like a network flow. So it's very widely used all across the baseband, all across the system. I'm not sure, but I think this is also used for the implementation of sockets on packet switch services. The memory management, you've got a heap, of course. Heaps, there is a global heap in the system, but actually I don't really know why it's not very used. In fact, each task implements their own heap. They reuse the same code, of course, but they have separate heaps at a fixed address, hard-coded address in the code. So the heap structure is very simple. The heap metadata will just keep track of what is the first block, what is the last block, and for each chunk block, you will see what is the size of the data and is the block free or not. So the next block is just the block after my block plus the size. There is no defragmentation process involved or complex things. It's very quick and efficient. That's all. So the nice thing, that you want to do is to debug the baseband. Because, I mean, for example, this is just a quick overview of the kernel of the system. And the system is made of a lot of tasks. You can take an image of the firmware of the baseband and statically reverse each task one by one if you want. First of all, the code is very, very dense, like horrible, and the main problem too is that a lot of interactions are involved at runtime between every task. So if you try to look into the baseband, you will see for a task big switches for the handling of signals, sending signals to other tasks and so on. And if you just look at it statically, it's almost impossible to understand what's really happening in the baseband. So you have to get some to see the system running in live at runtime, and eventually you would want to be able to catch interruptions. For example, if you are able to trigger an overflow or something, and you want to single step a task and follow the control flow and so on. How it's possible? Well, for code execution, getting code execution on the baseband, given what I've told before about the diagnostic mode, is very easy, obviously, because you have arbitrary read and writes in RAM. So, well, code execution is given, it's free. You want to upload your code, but you also want to communicate with your code easily. So the two main ideas would be either to hook an IT command or either to hook a diagnostic command. I prefer to hook a diagnostic command in my case because it allows me to debug the IT command. If my debugger is running in the context of the diagnostic task, I cannot debug the diagnostic task, obviously. So if I inject it in the IT command handler, it's the same thing. I could optionally, I could create another task in the system and be able to debug every task, but it's not very important because the diagnostic task is not a critical task in the system. I'm basically just reusing the future of the diagnostic task and using its own API to communicate with the payload over USB on the emulated serial port. It's possible to quickly get a code execution because actually only the first 12 megabytes of memory are marked as read-only in the page table, but the code section of the binary is 16 megabytes long, so there are like 4 megabytes which are writable, and luckily the diagnostic loop handling commands is in this range, so you can just rewrite the command table pointer, duplicate the command table pointer elsewhere, and get code execution through this, just hooking a command. So it's very easy. When you get code execution, if you want to write a debugger, next you want to be able to break a task. A task should be stopped if you instruct it to do so. The debugger tells stop this task, or if you hit an exception or a breakpoint. So you have to be able to unschedule a task and resume it on demand. For this, I just reuse the kernel API I've reversed before. So there is a specific function for waiting for a signal for a task. So I'm just using, well, I'm just telling a task, wait for this signal, and the debugger can resume the task by sending the signal to the task. There is a need that the signal is not used in the system in normal conditions. Otherwise, you would wake up the task even before you would have told it to. So what is done is that I have to execute this piece of code in the context of the task. So I could patch the code of the task and redirect the control flow, but the kernel directly offers an API to execute code in the context of another task with a DPC. So I create a DPC and send it to the task and tell the debugger tell the task wait for this signal. So if you want to, I don't know if anybody in this room has developed a debugger for ARM, I mean a software debugger, but in fact it's quite horrible because ARM has no native support for single step. It's quite crazy because if you want to do something as simple as single stepping a thread, you have the first way to do it is not like an x86 where you have the trap flag and you will trigger an interrupt at each instruction. There is no mechanism in ARM for this, so the standard way to do this is to predict the next pointer of the next value of the PC register, set a BP in memory, and resume the thread. So there is an obvious problem in this situation is that if you are in a multi-thread context, like here, you can't do this in a safe way because between the time when you put the breakpoint and the time when you order the task or the thread to continue, another task could have hit the breakpoint. So it would have to check if the breakpoint was meant for this task. So it can be done, but for example, if you single step into memcopy, it will trigger thousands of interrupts per second. Well, you don't want this. It's not reliable. So another way would be, of course, to you have the context of the thread, you emulate the instruction, and you update the context of the thread. Well, you need an emulator for this. The solution, which is offered by GDB in a multi-thread context, is to use displaced breakpoints. So it will use a scratch buffer where it will copy the instruction. It will put a breakpoint after the instruction, set PC on the scratch buffer, and resume the execution. In this way, you do not put the breakpoint in memory where the code is really relying, and so the other tasks can continue to execute without triggering exceptions. In fact, at first, GDB does not support some for this, so you have to recode it. And also, you have to, in ARM, you can address PC, so you have to take care of instruction relocations, like loading a value from PC, or using, if this is a jump, for example, you would jump out of the buffer and the breakpoint will never have been hit, so you have to account for this scenario too, and well, it's quite painful to implement. If you want something which supports ARM and SUMB, you can also, another solution will be to virtualize the address space for each task. In this way, you just put a breakpoint, use copy and write, and for the page where you put the breakpoint, and in this way, other tasks are safe for execution. But for this, you need to patch the scheduler and implement patch tables for each task, and it's quite painful too. So, well, my solution for the moment is to use a displaced breakpoint and standard too. So what is the debugger architecture? Well, you've got the stick, you've got GDB. I try to be GDB compliant. You are communicating over the diagnostic protocol, so well, you need some kind of a proxy to put the GDB request into your protocol, and well, you can also show each task of the operating system as a thread in GDB. So this way you can reuse the multi-threading features of GDB to debug the baseband. So I think I do a demo of the debugger. Wait a second. Okay. Just checking. All right. At first, well, I'm using the diagnostic mode to push my debugger into the baseband memory, and as I said before, rewriting a pointer to get access and code execution. So well, here it loads the thing. It will be finished soon here. I'm running the proxy. Okay, so the proxy is ready, so we can communicate with the debugger inside the stick. Now I've got a cross-compiled GDB for ARM, and I'm just connecting the proxy and the GDB client. And here it should work. Okay. So well, when GDB is connecting to the proxy, it will ask for the list of threads on the target. So here GDB is seeing the baseband tasks of the operating system. So well, you can see the name of the tasks. For example, you have the DPC task, the doc task. You have a lot of tasks which are dedicated to network protocols at various layers. You've got the main task, some hardware tasks like DSP, the vocoder, well, the NVRAM, and so on. So, okay. So when you debug the baseband, actually you have, as I said before, you have a watchdog task, which is constantly checking whether tasks are alive. So if you break a task, for example, with a breakpoint or something, the watchdog, will detect it and reboot the system. So you have first to account for this and break the dog task. So I'm going to. Okay, so here I'm getting into the context of the task and interrupting. Okay, so the task is interrupted. I can check its registers. I can check its code and so on. You can also well, indirectly inspect anything in the baseband memory, obviously. So, for example, if I call Rex self, sorry, which is the API in the kernel to get the current task, the current task structure. So here I'm calling it. So okay, I get this. Now I'm printing it. Okay, So as you can see, well, if you can inspect, you can do the same thing for the heap. For example, my debugger has a separate heap, so you can inspect structures very easily. Here you can see that I'm really calling this function in the context of the doc task. You have the name in the field directly in the task structure. So now for breakpoints and blah blah blah. Just a second. For example, I will. Okay. So here is just an AT command handler for the SGSN AT command. It's just a command, an AT command to get the email of the phone and the serial number of the manufacturer of the mobile. So well, just putting a breakpoint on it. I don't see my screen on my computer. It's kind of. Okay. Here I'm in the IT channel. IT plus SGSN. No, not CGSN. What? Okay. So here I've hit the breakpoint. If you look at the tasks, you can see which task, in which context I am. It's quite slow because GDB is doing a lot of useless stuff. Well, here it's in the data service task, which is handling the AT commands. So I'm getting into its context. Okay, get access to its registers. I can check its parameters. I can see, as you can see, this is the right task, and well, I can single step into it. Okay. Well, it's also nice for catching exceptions. So, well, going back to this, well, I'll get back. I like to use the watchdog task for my experimentations because when it dies, nobody cares. So, just calling, for example, a function which appears to have another Stack Overflow, an obvious Stack Overflow into it. So, well, just a name copy on the stack. Here. Okay, and here you get this. So, yeah, you can see that you have rewritten EIP, get a backtrace. Well, the backtrace may not be accurate anyway in GDB because it has no way to distinguish between code and data. So I suppose it uses heuristics to find this. Well, so if you find, well, if you use this thing, so this debugger, and you fill the USB key, you can catch interruptions and see the context, the task in which you are. Triggering the exception. Yeah, and there is also a nice possibility with this way, because this way of doing, because when you get code execution on the stack, well, on the stack, code execution on the baseband, you can also directly pass command to the baseband, and so you can, instead of deploying a huge, not huge, but like deploying a BTS and doing radio frequency fusing on the baseband, you can inject data locally on the USB key. Possibly, well, it could be possible to fuse the baseband with no BTS at all. Just passing commands to the debugger and transferring, making the right function calls. Well, you need to know which function you want to fuse, of course. Okay, so in conclusion, baseband systems are still massively used and poorly known. There is no much literature nowadays for seeing how is architectured a baseband operating system. The nice thing about the Icon 225 is that it uses a non-secure bootloader, so you can easily reflash it if you know what you're doing. There is also easy code execution achievable, so it's nice for reverse engineering. But you have to know that the more recent versions on phones today use an OKL4 Rex hybrid kernel, so it's not exactly the same thing. As far as I've seen, the L4 kernel is just used for the scheduling, but the Rex kernel remains for everything else. Of course, on smartphones today, you have a second processor with interactions with the application processor. So, you can see some related tools, the Philip Veman baseband apocalypse last year, Luis Miras talking about baseband playground on Infineon unlocking. And on the web, you have various communities. You have TG World, bb.osmocom.org for Osmocom BB, and many communities like XDA developers and so on. Interesting. Okay, so thank you for your attention.
Yeah. So, thank you for your talk. I just want to ask you to please sit down until the questions also are done. And if you leave, please leave through the front door and take your trash with you. So, questions? Here in front.
So, thank you for your talk. And a question regarding the base. Have you seen JTAG lines or something? So, for example, if you try to mess around with the flash, you need an emergency exit. So you can, for example, rewrite the flash with a JTAG debugger. So if you, for example, have a costly commercial JTAG debugger that can use the ARM device, so you can always reflash the device. So if you mess around with the flash, you have a brick device.
Yeah. You mean through JTAG or?
Yeah. Have you seen some JTAG lines, or have you looked for this?
I have not looked for this. I know there is a JTAG which is connected directly to the ARM processor, but to the flash, I don't know. I have not looked into it.
Okay, because it would be interesting to do this. But
you can reflash the NAND through software calls, so you do not need hardware.
Yeah, but for example, you can hook up debuggers like from Lauterbach or other companies who make book debuggers, and then you can just debug via JTAG.
Yeah.
You can debug the device via JTAG. It's a normal way to debug a device.
Yeah.
Do you have the trace cell that is connected to JTAG inside the chip, and then you can debug with a JTAG debugger.
Okay.
And so if you messed up everything, you can just write the flash again.
Yeah. But I don't know, honestly. I have not looked for it. I have not tried to reflash the device for the moment. I'm just, as you saw, I'm just pushing the code in the RAM at runtime.
Yeah. I've got two questions via IRC. The first one is the baseband you analyzed identical to the embedded basebands of Qualcomm's MSM 7000 or Snapdragon chipsets?
Are they? Sorry?
Whether the baseband you analyzed is identical to the embedded basebands in the Qualcomm MSM 7000 chips or Snapdragon chips?
No, I think in 7000 you have a RIX L4 hybrid kernel, so it's not exactly the same thing. But,
And then,
the system is, you know, they have not rewritten the system from scratch. They have just changed the kernel. Well, I think if you find, I don't know, but if you find a vulnerability, for example, on this stick, there is some fair chances to find it in other versions, whether or not the kernel is different.
someone is asking, how long did the whole process of reverse engineering this take?
This, honestly, maybe for reversing just the kernel, maybe 5 days, maybe. But just gluing all the things together and testing, developing the thing, 2 months.
Okay. And could you please put your slides and the URLs on the pentabarf?
Yeah.
That would be cool. Thanks.
Did you have access to any documentation, any papers of Qualcomm? So like user manuals for Rex or something? Like
there is, I know there is some leaked documents from Qualcomm on the internet. Well, I've looked into them, but the thing is, something interesting is that you have the Rex sources, which has been leaked for a very old version of Rex. But from what I've seen, what is in this USB stick is much more complicated than what I saw in the sources. So it's looking alike, but not the same thing. And it's in the baseband documents. There were a lot of leaked documents, but I have not go through all of them. So it's good to check on them to see if you are on the right path, but not.
I have two questions. First of all, the agenda was to find out interesting things about the Qualcomm baseband. So I'm wondering why you are not using the Qualcomm diagnostics tools that are more or less freely available on the internet, which seem to have leaked from Qualcomm licensees. So your work is somewhat different and it's impressive, but why not try this first? So, and the second question is, are you doing this privately for fun, or are you doing this through your company with some agenda?
No, I'm working for a company. I'm working at Sogeti, which is a French company, and but that doesn't mean I do not work for fun. I mean, I'm doing it for fun also. But in fact, the first idea I had when I started looking into this was not to find vulnerabilities or developing a debugger, but developing more of something to dump the data, like at various network layers, just to see without deploying BTS and something, just to see what the network data would look like in telephony protocols. So I find this interesting to be able to dump data on this key. But well, as a matter of fact, I realized for reverse engineering I needed a debugger, so I first developed a debugger. And there was two questions, but the first one was.
Well, why not use the tools that are available on the internet, like QSTM or so? You can find this in several places.
Sorry, can you repeat?
Which attach to the diagnostics port you mentioned.
Yeah. What is available on the internet? Sorry, maybe there is something I haven't seen. So.
If you Googled it, you'll find it.
Yeah, you mean the diagnostic channel, for example? Or everything?
No, the tool for it, which is called QXDM.
Well, maybe, okay. It's not very long to reverse, actually.
I had a quick question. We noticed some symbol names in your in the GDB output. Are those your symbol names, or did you find a symbol table within the binary?
Actually, I'm in my GDB. in its script. I'm just loading my debugger. I include the symbols into the binary of my debugger in ELF, and I load it into GDB so it can look into them.
Okay, so those are your symbol names, though, not official ones.
No, that's my one.
Thanks.
So, are there any other questions here? Oh, there are two, I see.
Another question from IRC. Do you plan to release the source code, or is there a possibility to get the source of your tools?
Yeah, I have not done it yet. I will upload it to Google Code IZIP.
I think you hinted at it. Are you actually working on a protocol analyzer? Is that what you're actually building?
Sorry.
You sort of hinted at it, but didn't actually say. Were you actually working on a protocol analyzer? Was that the sort of initial starting point?
Yeah, actually it was.
Did you have any success in that, or is that something you're still sort of working on?
In fact, for this, I'm just the debugger is not finished. It has basic debugging capabilities for the moment, but there is a feature I need for this. It's the implementation of trace points, so the ability to not to resume a task immediately after hitting a breakpoint. And for this, it's not very evident because you have to displace the instruction and execute it elsewhere, so you have to perform relocations and so on. And my relocating motor engine is not completely finished yet. So as soon as I get trace points working, I will put trace points on sockets in the basebands, and I will try to see what comes out of it.
Yeah. So, thank you, Jan. We are now at the end of our time, and it was a very interesting talk, and have a round of applause.